Let's figure out what that means. Hello everybody, thank you for the introduction. Today we're going to talk about such an interesting topic, invariant risk minimization, which was proposed by Martin Arjovsky in this article. And let's start with a simple example. So imagine that you had a simple classification task. You wanted to classify between cows and camels images. So what's the problem? I just take a convolutional neural network, a bunch of images of cows, a bunch of images of camels. I feed forward, backpropagate, and eventually I receive a model with a very low training loss that seems to be able to predict between cows and camels. So what can be the problem? Well, the problem is in this image. It seems that the images of camels have this, sandy beige background, whereas the images of cows has this green, grassy, nice landscapes. So basically, our network just cheated. It averaged the color of the background and predicted the output. And this feature is really very strong, but it's spurious. It's not the natural cause of things, not why images actually are images of cows or images of camels. And here we come to the classical correlation-versus-causation dilemma. You see, our modern machine learning algorithms tend to absorb all the correlations they can find in data. And in data, we can find a lot of spurious correlations that are induced by various biases. Those biases can be some random factors or our way of collecting, processing data. Anything else? Anyhow, we always have these spurious correlations in data that we don't want to learn. And we have a very non-trivial problem. We want to identify those properties of our data that describe spurious correlations and get rid of them, and identify and use useful properties that represent the phenomenon of interest, like animal shapes in our example. So what will be? So we can notice that those spurious correlations are not stable. They tend to vary from data set to data set or from environment to environment, whereas true causal features, properties, are invariant. They are stable. They present in all environments, in all data sets. So we can use it to build predictors that will generalize well for new testing environments. And by the way, the authors of this article also notice that shuffling that we commonly do in our for our training is not that okay, because by shuffling we destroy the information about how the data distribution changes from data set to data set, and hence we can no longer follow up on which features are stable and which features are not. So we make our lives more complicated.
Are you referring to mini-batch shuffling?
No, just shuffling of data.
Shuffling of data sets, just the order of examples?
Yes, because we have a very strong assumption about the identically distributed independent data. But when you collect your data objects from different environments, they are not identically distributed. And when we mix them and receive one big data set, we destroy this information about how it changes. But that's just a side point stated by the authors. That's not the main idea.
What you're afraid of is just you have a single data set, but it's collected from different environments.
Yes.
And you don't want to shuffle the environments, actually.
Yes, you don't want to shuffle data from different environments into one big data set. Okay, so what will be our strategy? We will assume that our training data is collected from several distinct separate environments, okay? And we will promote learning such algorithms that will absorb only stable correlations across these training environments. And we will hope by that they will generalize well for new testing environments. So in our example, that will be very simple. We can just for instance, collect cause images from different countries. As you can see, cause in Holland always pasture on such juicy, greeny, grassy landscapes, whereas cause from Corsica actually have background very similar to images of camels, right? And using these separate environments with different landscapes for cause images, we can hope that our invariant promoting algorithm will notice it and get rid of this strong but spurious correlation. Okay, here we come to the spotlight of the paper, the principle, the invariant risk minimization principle. So it says that in order to learn invariant predictors, we need to find such a data representation that a classifier on top of that representation would be optimal in all environments at once. So I understand that this is not clear at all by now, but by the end of this talk, I hope that things will get more apparent. So let's be more concrete. The basic formulations. So we consider that we have several data sets. As I said, they are collected from different training environments that are a subset of all environments possible. And our goal is, as always, to predict output from our inputs, right? And we will promote such a minimization, such an objective to minimize. It's basically it's maximum risk across all environments we have. So you can see that RE is just empirical risk in environment E. So why that goal makes sense? Let's consider the following example. So I'll write it down because we will need it further on. So we have two input variables, x1, which for example is Gaussian with varying noise, output, which causally depends on x1 plus some varying noise, and the spurious variable which depends on the input plus some fixed noise, for example. So basically our environments can vary in first of all in the magnitude of the noise, of course. As you can see, for example, we can have two training environments with two different magnitudes of noise. And also, the author states that we can vary the structural equations for our input variables. For example, for x2, instead of this equation, we can have something like, I don't know, y squared plus some Gaussian noise, or just a constant 10 in 6 degree, anything you want. The thing that remains stable is this causal correlation between x1 and output y. Okay, so we have this set up, and we imagine that we are just building a linear regression on top of it. So we can regress from only x1 from our causal variable and obtain these coefficients, 1 and 0. We can regress just from x2, the spurious variable, and obtain the following coefficients. And we can regress from both and obtain those coefficients. So you can clearly see that only the first regression actually is stable across even our two environments that differ by the magnitude of noise, whereas the second two are not. So we can clearly see that the true causal dependency between x1 and y induces invariant linear regression. And so yeah, that's what I just said. x1 is... Yes?
I haven't actually get why previously.
Mm-hmm.
By regressing from x2 is bad.
Well, because you have, it's bad, we'll see it in this statement, because the first regression, this one, from x1, the true causal variable, this is the only regressor that has finite out-of-distribution risk. That maximum empirical risk across all environments. Because, as I said, we can vary this structural equation. And if we have a testing environment which has a very high x2 variable, we will have infinite error, infinite loss. You see? So,
well, it's not clear because if your x2 in testing environment is again just y plus some noise, it would be very good to return
yes,
from x2.
but our out-of-distribution risk is, I will return to, is the maximum risk across all environments. So in some environments it will be okay. Actually, in our training environments, those regressions are much better than x1 because our noise in x1 and here is much higher than in our spurious correlation. You see? So just...
Does it mean that in the training set you have only one environment and different environment in the test set?
Yes.
So it's kind of there is a clear mismatch between the two distributions.
Yes, yes, that's exactly...
Using multiple environments for training.
Because we cannot have as much environments as we want. We only have several environments.
But doesn't this mean that here it's like a clear data collection problem? So it's like one should not be solving a problem like that if it's if you need action to solve the problem.
Well, we can solve this problem. This is what this article is about. So even when we have not all environments possible, when we have just a subset of training environments, we can actually identify which dependencies are true causal and which will vary from environment to environment, which will not generalize. So let's make it clear. Yes? I'm sorry.
So again, that's the question. Is this ROD is a good quantity to minimize? So if you have like the environments of non-equal sample size, so you have the environments of different sizes. So and in the small environment you have a large error. So your quantity will force you to minimize your error on the small environment.
Yes. Well, basically, this example just shows that this out-of-distribution risk is something that makes sense if we want to search for true causal dependencies in data. We can reason on this for. We can find some drawbacks of this loss. Basically, it's maximum loss across all possible environments. It's absolutely infeasible in practice to minimize such a loss. But in this example, this loss actually helps us to fetch the true causal regression. Because all the regressions with non-zero x2 coefficients would have infinite, as we can vary this structural equation, infinite loss. So that's more or less clear, okay? I hope it will be more clear further on, because...
Very simple
No,
question. We have several environments. For example, with car, with cows, we have cows in one country and in another country. Why can't we just mix all the data? I mean, in this case, you will not, you already will not think that cow may be only on the grass, because it sees a lot of pictures with cows on sand in different country, not on the grass.
Yes.
So why this is better?
Better than
why
what?
can't we just mix all the environments together?
Well, because if we mix all environments together and we will minimize just empirical risk across all environments, for example, okay, here we have these two environments. If we minimize empirical risk, we will receive this regression, right?
Minimize this in one environment, not in both.
In both, actually.
But you have E. What is E then? Like E
is environment this noise?
There is one E and not two E's.
Well, you have two environments, two data sets. Each data set is collected from its environment. And then to minimize empirical risk, you unite them, maybe shuffle, and then you build the regression formula for a regression equation. And you will receive these regression coefficients.
But why is it, what is E? Is it like first or second?
It's one environment.
Because before you said that we were training in one environment and testing in another environment.
No. We have several environments to train, but we need to use them more cleverly than in just empirical risk minimization.
So in the last line we have x1,
Mhm.
which is one variable, and x2, which is another variable, from the same environment E. No?
Well,
There are two environments here.
okay, I guess that this index here is, well, it means that,
But x1 and x2 are the two features. So there are two features, and
Yes.
they are correlated. They come together. So if
They are
one,
in the same environment.
yes, but you can have multiple data points from different environments. Yes.
yes, as you collect, you see, you collect your data sets from different environments. So you have several data sets, each one is collected in its environment.
Okay.
So does that make sense? More or less.
You do what I said that you can do. So you just mix all the data together and
Mhm.
train on this data.
Yes.
And why is this that?
Because you will,
Why is it dependent on E? What is E? That's not clear.
what, here?
First time you get the data points two numbers, x1 and x2. You need to regress.
Yes.
You don't know E.
Well, okay. If you mix, you will not have this index E here. But if you regress in each of these environments, those.
If you train in one
We
and
did
test
it in
another,
E is like different sources of data for training.
E represents different environments. It's the
yes,
environment.
okay, but
iterator.
at the test time, there is no E. We don't know which environment the data point comes from.
Mhm.
Otherwise, there is a third feature which tells you the environment.
Would you please answer to my question? We mixed them. Why is this bad? I don't understand because there is no answer on the slide
I'm
for this
sure
question.
that what you are suggesting, that's a baseline. That should be different. So that's a one-way train.
And at the end we will see experiments
Yeah,
and
probably
say this
the
will
method should be
work
doing
better.
better than this.
But like, do they have some intuition? Why?
Why what?
Why we shouldn't just mix all the data together?
And
Because
we
your
will
example about
discuss
house.
the next slides.
Yeah,
Yes.
maybe if we let him continue.
Yes,
he
that's-
will explain more of what's to come.
Yes, exactly. That's what I
mean,
want.
Your example is house didn't answer for this question. That's
The
only
answer
reason
is
why I
because
have
we
the
can
question.
have camels on the grass also.
That's a good point.
Thank you very much. Okay, so if you don't understand any details by now, it's okay. We will go further on, and things will get, I hope, more apparent. Well, at least you can look at the paper. It's a very good paper. So if you want to really dive into it, I encourage you to download the article. So okay. Now, about how we can solve the problem of generalization or like prior work. The first one is simple empirical risk minimization, right? But it doesn't work in our example because for empirical risk minimization, we have training environments with very high noise with the variable x1. So our empirical risk will promote correlations with x2. And then when we will receive a testing environments with very high numbers of x2, for example, absolutely different structural equation that we didn't meet in our training environments, we will have infinite or a very large loss, empirical loss. So empirical risk doesn't work here, okay? That's okay. Is it clear why it doesn't work in this example?
No.
So you sum over environments here with empirical risk.
Yeah. So empirical risk minimization, just it's a simple strategy when you just want to minimize the sum of empirical risk in first training environment and empirical risk in the second training environment.
When we mix all the data together.
And
Yeah.
your proposal is to take the max and minimize the max of the
That's what is proposed initially. That's our super wanted goal, to minimize the maximum risk over all environments. Because if we will have such a predictor that minimizes our risk across all environments, it would be good everywhere, in all possible environments. But that's an infeasible optimization task for us by now. Okay, so empirical risk doesn't work, really? Yes? Well, believe me, it doesn't work. Next, we have such an approach.
We're looking at these two things. So, y depends on x. There is a correct causal dependence, but the noise is high. So you have a normal distribution with a sigma, which is like 10. Like 10, which is high. But then you have anti-causal dependence on x2. But then the noise is very low. So x2 is almost equal to y. Why isn't it a good idea to just give x2 as an output?
Yes, that's what empirical risk would do. Empirical risk.
Why isn't this the best possible strategy? Because correlation, in terms of correlation is much higher. Why do you care about causality if you just do prediction?
Because in training environments, because you trained on some.
You might have spurious correlations. You might have camels on green grass and cows on sand. And then, with your model learns to classify
I understand
grass
the
and
camel
sand.
example, but I don't understand this example.
This example, I'm explaining. So, okay.
There is a big gap in between.
So is it clear then that if you minimize empirical risk in this for this model with very high noises, you will promote learning from this variable, right? X2.
Okay.
Then you have testing environments which has something like this equation. So it instead has a very low loss here, noise here. The same. It should have the same or similar up to the noise magnitude structural equation here, and then it has x2, which is basically constant, and it's 10 in 6th degree. Then your predictor y equal to x2 would have super high loss here.
That's super. You change the structure of the problem. So you
Yes.
just remove one of the dependencies. So it's like if you're training on one model, in one environment, and then you're getting something totally different, which has no connection with the
Yes,
previous one.
it's not totally different. It has.
No.
It's not.
Why there is no dependency of x2 on y with the same last line? That's what I would buy that one. Okay.
Because this is the spurious correlation. Because we are trying to find causal dependencies. Like in Bayesian network, if we build a Bayesian network of this model, we will have something like this, or exactly this picture. So the causal correlation, which should not, this is our main assumption here in this article. Our main assumption is that this connection does not does not vary from environment to environment. We can vary like these noise connections or this connection. We can vary, but this remains stable. The causal. This is an inductive bias, of course. This is our assumption, but it seems to be something reasonable. Okay. So now robust learning. So okay, empirical risk doesn't work, unfortunately. Robust learning. Well, robust learning seems to be something very close to the out of distribution risk, because you see that we also maximize our empirical risk, but now we maximize only across only across training environments minus some like it's called environment baseline. This environment baseline helps us not to focus too much on noisy training environments, whatever that means. But it turns out that, and we will and we will show that very simply, that this robust learning is actually a weighted version of empirical risk minimization. Because you see that if we want to minimize across all the predictors the maximum risk of this predictor, this is basically the following constraint optimization task. We want to minimize across Fm, M, where our, I forgot the baseline, where our risk minus baseline is that okay? That's okay. I just rewrote this in a similar, in equivalent.
Problems with the same E for the maximum variable and for this particular small r. So you should have E hat or E star, some specified environment.
No, I maximize here across some. Okay, some.
So you maximize the subtraction.
Should have brackets.
I try to minimize this this thing. I try to minimize.
You're minimizing the difference between the risk and R and the baseline, right?
I try to minimize this thing.
Yes, you just needed some brackets.
So I minimize across. I minimize the maximum.
No, the question is about what you have under maximization. You have either difference between two terms under maximization, or you have a difference between maximum and small r.
And what is small r and curly e? Those two new symbols.
Okay, let's follow the line. First one, what's exactly the problem?
What is small r e?
Small re is some constant that depends on the environment. So in each environment, in each training environment, it would be just a scalar value that we subtract from the I need brackets
Yes.
here.
The question was about this.
Yes, here there must be the brackets. Okay, so I'll put it also here. Okay.
What is small r and the curly e?
What is this thing?
Yes.
It's called environmental baseline, and it's needed for not focusing too much on noisy training environments. But that's another paper. It's not this invariant risk minimization.
Is it a constant which is unknown for some environment, or is it like?
It's a constant. It's
unknown, some unknown constant. Yes.
yes.
Or is it assumed to be known?
We try. Basically, we can try to approximate it, like in reinforcement learning, in reinforce algorithm, we add a baseline, and there are several techniques for this, but I'm not familiar with this approach.
But that's an optimization tool to reduce variance of the gradient estimator. And here, that's like some constant. It's like a constant which depends on the environment, the property of the environment.
Yes.
But is it known or not known?
No, it's not known. We select it. Usually we...
Basically, robust learning is trying to minimize the biggest difference, minimize across all environments, minimize
across all
environments.
Predictors.
The difference, E's environments, no?
No. Yes, it's environment, but robust learning tries to minimize across all the predictors that maps inputs to outputs.
Yes.
And what it minimizes? It minimizes the maximum baseline subtracted risk over all.
Basically, trying to minimize the biggest error across all, across all the different environments. We're trying to find the place where it's making the biggest error, minimize the biggest error.
Yeah.
Cool. Okay, but does this mean that you need to have access to all environments at training? Because if yes, then why not, the previous examples, then ERM will work as well, if you have all the...
Yes, of course, but that's why we need these baselines that will... Well, that's just an approach. And I'm going to show that this approach is equivalent to weighted ERM. So we came to the constraint optimization task, right? Then I write KKT... so just the derivative... So I just put the derivative of my Lagrangian to 0. And that derivative with respect to f, to the predictor. And that derivative basically is sum by E of gradient of lambda E by gradient by f of, and we assume that our risk is a good convex function, and this is equivalent eventually to f, on which we have 0 gradient of Lagrangian is actually an argmax and argmin across all the predictors of that weighted sum. Okay? So basically, this is the weighted version of empirical risk minimization. Right? Those are empirical risks in environments, and for empirical risk minimization, we would have those lambdas equal to each other. Right? And this is just like a modification of empirical risk. So this will have the same drawbacks as empirical risk minimization for our task. It will also promote learning spurious correlation. Okay.
But I don't understand why you say the lambdas are not necessarily equal. So maybe some examples where cows are in the desert will have much bigger weight.
Yes, it may have much bigger weight, but it depends on how we choose our baselines. And we're not talking about now. We're not talking about that like imaginary example with cows and camels. We're talking about this example, very simple example. But it's, as we see, we already have 2 methods that can cope with this problem. Now the third one is promoted by many different authors. For example, by Viktor Lempitsky. Domain adaptation principle. We want to, well, the formulation is very simple. We want to find a data representation which has the same distribution across all environments. Okay? But the authors of this paper claim that this may sometimes lead us into wrong type of invariance. And actually they dedicated the whole section in their appendix to explain why domain adaptation is not good. But in our example, it's obvious, because the true causal variable x1, it has varying distribution across environments. So our invariant representation of data will not be, as we want, x1, 0. And it will not work for us as well. And finally, so-called invariant causal prediction. The idea is to find a subset of variables such that the regression, the linear regression on top of that subset would have equally distributed residuals across environments. Okay? So basically, this is somehow a state-of-the-art method before this one. Which I'm about to present, and but it has several drawbacks. For the first one, it's always assuming linear regression. The second one, it searches for a subset of variables, and searching for a subset of variables in a high-dimensional tasks is absolutely infeasible. And the third point, it also doesn't work for us because we have varying noise from environment to environment. So invariant causal predictor will also not help us to learn the true causal dependency of y from x1. So it seems that even for such a simple problem, we cannot find the true causal solution. So is everything all right by now?
Well, you can transform your ROOD using the same procedure with constraint minimization.
Yes, I can transform. But it's, as you can see, here we have only a subset of environments, not all environments. So I can also transform my out-of-distribution risk into a weighted empirical risk, but across all environments. If we have all the environments possible, it's okay. We can learn empirical risk minimization predictor. It would work fine. It would actually be optimal for us if we had all the environments. But when we are constrained to several ones, we cannot afford this. So yeah, it seems that even for such a simple example, all the state-of-the-art methods in causation learning seem not to work. And here we're approaching the formulation of invariant risk minimization. But first of all, we need to define what are actually invariant predictors. So I say that, for example, assume that I have a data representation which maps my inputs into some space H, and I have a classifier on top of that representation which maps H to my outputs, and I say that my predictor W by phi is invariant if and only if my classifier is the optimal one across environments from some set of environments over no, not here. Across all the classifiers on top of that representation for each environment. So that's basically the definition of invariant predictor proposed in this paper. Well, the authors claim that this is something reasonable because it actually reflects the concept of induction in science. Because you know that, for example, in physics we're not focusing on concrete objects representation. We try to find some abstractions. For example, for the gravity law, it doesn't matter whether your objects are apples or stars, planets. It doesn't matter. We try to get rid of everything irrelevant for us and just leave useful causal features. So that's why philosophically this definition is something that really reflects invariant predictors. Is this definition clear? Okay, so now we proceed to the formulation of the
domain adaptation. Because say within like normal domain adaptation technique, you would be trying to find such a data representation. Given that, you cannot distinguish between environments. So like distribution of feature vectors within this representation will be the same across environments, indistinguishable.
Yes.
Does this mean that this implies this definition?
No, it does not, and actually those things are really similar. And as I said, the authors provides the whole section of discussion on this topic, why domain adaptation and IRM are absolutely different things. But simply saying why domain adaptation is something we don't want is, for example, say that we have one training environment and one testing environment. So, for example, so we have X collected in training environments and out.
You need at least 2 training environments. You need source.
You can use access from the testing data set in domain adaptation.
Sorry, is the basic idea is that for domain adaptation you need to know you need to know your target domain, and here you're trying to be domain invariant to begin with. Isn't that the basic idea? And a domain adaptation, like, okay, I've trained my speech recognizer on English with an English accent, and now I'm doing speech recognition of English with an American accent. I know that I'm doing it with an American accent. I've adapted to that information. Or I can make a speech recognizer which is invariant to the properties of accent altogether. And isn't this the basic difference?
Well, this is one of the differences, yes, because it's much more general thing, this one. And in domain adaptation, you actually really want to adapt for a new known somehow domain, for a testing set. But in domain adaptation, you actually don't care about the outputs. So if your test and training environments have the same distribution of access but different distribution of outputs, then your domain adaptation would fail, because
so you basically adjust for covariance shift.
Yeah, domain adaptation is for covariance shift basically, and this one is a more general thing. So yeah, the formulation of IRM, basically it's again a constraint optimization problem. You see that we are trying to minimize across all the accessible representations and all the accessible classifiers. We're trying to minimize empirical risk on our training environments, but we are constrained to use only invariant, according to this definition, only invariant predictors. So we're minimizing our empirical risk across invariant predictors. Because, for example, we can take zero constant predictor, it would be invariant, apparently. Because it's constant. It's even on intuition sense, it's invariant. But it will be useless. So we're trying to solve the min-max problem. We're trying to get rid of everything irrelevant and leave only useful features for our prediction.
Is there a strong assumption here that you have a predictor which is invariant across all environments? You
exactly.
Assume existence.
Well,
because you have this set, there should be a vector which belongs to this set for all environments simultaneously. It should exist.
Mm-hmm.
Otherwise, it's just empty.
This is a very good point, and I also thought of that. But you see, the authors say that this is just a theoretical formulation of IRM, because it's impractical. We have very strong constraints. They are infeasible in practice. And for practice purposes, we have this version of IRM. Yes.
So you have a constraint optimization problem, but I haven't get why can't you just take this W from RV minimum, and this would be the solution, the invariant predictor?
Because as I said, you can zero predictor would be invariant. It would be argmin across all zero predictors. Yes. I mean that, for example, consider.
Okay, if your feature extractor is just zero, then zero predictor is. But okay.
Well, not zero predictor, but a constant predictor. Yes. If you map your inputs just to zero, so you destroy all the information of your inputs, then a simple constant classifier, as it's called, would be invariant. You just take the mean of outputs.
Can't they just take not the arg minimum of RE, but arg minimum of a minimum over 5?
Well, I think that's they do not make this thing clear. I mean, they do not have this point in their article. Like, they have just this formulation of invariant risk minimization, and then they try to develop it. So it's basically trying to, again, minimize the empirical risk, but subject to invariant predictors. Not all invariant predictors are good, but those that are good are will be good in all environments.
But if this constraint is satisfied, doesn't mean that we only need to solve the optimization problem with respect to phi, rather than with respect to W. Because W is already...
Yes. As you can see, we have no minimization in our practical version of IRM, and we're going to discuss it.
Can you fully explain that equation?
This one?
Yes. Can you fully explain?
We're gonna move to it. It's gonna be fun. So those things happen to be related, but it's absolutely not clear why. And we're coming to the trip from IRM, from the classical formulation to the practical one. The first step will be very simple. We will just rewrite our constraint optimization problem into soft constraint problem, which is just penalized with some regularizer, which actually this regularizer is penalizing us from being not optimal in environment E. Okay, that's what his purpose. And we assume that it's nice, differentiable function, etc.
And the first term is just empirical risk.
Yes, this is the same.
Right,
We just
empirical risk plus regularization.
Yes.
And the D inside of is inside of this.
Yeah. Because we have E, so there should be parentheses here. Okay, very simple. Now we assume that our classifiers, those W, are always linear. This is a very strong assumption, and we will talk about that a little bit later. But okay, for now we assume that we will only deal with linear classifier and arbitrary data representation. So consider just a linear least squares regression. Then we can analytically write the optimum, and we can propose a very simple penalty.
In correct brackets, the first part, you should first take an expectation and then inverse.
Well, yeah, you should have also. The authors of this paper do not like parentheses. Yes. So you can just propose the following penalizer, which is very trivial, just a squared norm distance, square distance towards the optimal solution. But you see, we have this matrix inverse here, and it's not very nice thing. So we will just multiply both terms, both vectors by this matrix, and we will obtain a similar penalizer, but it will have much nicer properties that are depicted in this figure. So what is represented here? Basically, those are plots of two penalties for the same example as we had. Assume that we are trying to find a very simple representation that will be as follows. We will remain x1 as it is and multiply the second component by some constant c, which is parameter of our mapping. And we remember that our optimal solution is c equal to 0 and opt is 1, 0. Okay? This is the true causal predictor that we want to learn. And here, basically, we have the graph, the plots of those penalties for different values of c, for different magnitude of the second spurious component. So we measure the distance between the solution given for the given C of empirical risk minimization of least squares regression and the optimal classifier 1, 0. Okay, so we can see that the second penalty behaves much better than the first one, and even the first one in a very regular, in a strongly regularized. For a strongly regularized linear regression. So we will use it further on. So that's clear why this thing is better. Well, basically because we got rid of the matrix inverse here, but the authors also provide some graphical intuition on that. Okay, so now, okay, we have regularized optimization problem with linear classifiers, and our penalty would be would have this form. We go on. So we can see that assuming linear classifiers, we have overparameterization, because for a given pair of classifier and representation, we can just multiply them by some invertible transform psi and receive the same predictor, right?
Can you
So
please explain this circle notation?
circle is just superposition of function. Okay? So you just apply one function after another. Okay, let's just constrain ourselves. Very simple. We will assume, we will fix some non-zero classifier tilde w, and just optimize only across representations, such that the optimal classifier, again on top of that representation, has this non-zero value. So we got rid of the optimization across classifiers.
W tilde is just arbitrary vector.
Yes, we just non-zero. We just fix some non-zero vector because we can. It's clear from this equivalence. So it seems to be like reasonable. Okay. Now the fourth step. Well, basically that means that we can just take the first basis vector and use just the first component of our representation, and everything will be all right. So we will receive this optimization. So we will receive this optimization problem eventually. And by now, probably you ask yourself, what's going on? Is everything all right? Didn't we mess up somewhere? So the authors provide the following theorem, and it's a very simple theorem. Don't worry. They have much worse theorem, but we will not touch them. Don't be afraid. So I would like to first formulate it more simply.
Sorry, before you begin, W are the weights of our model?
It's a linear classifier on top of our representation.
Right, so it's the weights of the Phi's.
Yeah.
Right, it's the vector we multiply
It's
by enough.
It's like in neural network. You map your inputs to some final layer, yes,
Yeah.
and then there is just linear regression on top of it.
Yeah, okay, I got it, yes.
So that's an intuition. Okay, so the theorem actually makes things clearer for the linear case. It actually says us what are invariant predictors in linear case. So we say that we have x's which belong to Rd and one-dimensional y's, and the set of linear invariant predictors. Yes, the predictor is just linear regression, so it's just V transposed x equals y. So the set of such V's that are optimal, that are invariant, and according to definition, what that means? That means that we can represent our V as some phi transposed by W, where phi belongs to Rp by D, and W belongs to some Rp, such that our classifier is optimal across all environments. So, such that W is argmin across all the W tilde from Rp of our risk of phi transposed by Wp for all environments from some set of environments. Okay, and this set of invariant linear predictors is actually the set of such vectors from Rd that are orthogonal to the gradients of risks.
Equals 0 or what?
Yeah, sorry. Okay, well, a very nice theorem. It makes things more apparent, at least for the linear case. And I will define this as G, E, V, okay?
Maxim, what is the first dimension of phi capital P?
Where? Here?
Phi capital is from real matrices, like
Yes.
P times D. What is P?
It's some number. We will see it. Well, it can be 1 actually.
So for one object it is 1.
No, it's not. It does not depend on the number of objects. It's just some number. So this theory means that the optimal linear classifier predictor, which can be represented as some matrix, or for some p, as phi transposed by W, where W is argmin of risks across all environments, is actually the set of vectors which are orthogonal to the gradients of risk. And
Phi's are the same. An expression for V and an expression for W.
no, for here there exists.
Not here. Line before.
Okay, so for this set of V, of vectors V, there exists such matrix phi, such a number P, such matrix phi, and such vector W, that V is phi transposed by W, and W is argmin of risks. So let's prove it to make things actually apparent. So here I will prove the necessity. And okay, so what actually means that W is argmin. Okay, I rewrite it. Across all the W's from Rp of risk in well, basically, okay, we assume that our risk is convex, so we can rewrite that in similar gradient manner. So it means that the gradient with respect to W of risk.
Could you please use one letters?
Yes, I'm sorry. W of phi transposed by W is 0, and I take the derivative. Basically, this is just phi by the gradient with respect to V of Re, this is V, I remind you, of V, okay? So this is the 0 vector. Then I multiply this 0 vector by W from left, and I receive W phi WV RV is 0.
Should be W transposed.
This should be transposed, and this is V transposed. So we have shown this part. Yes? Okay, now the sufficiency. Or I don't think that you will see it here, so we will not actually need it anymore. I just wanted to show it. We will need sufficiency to explain our ideas.
But isn't the proof almost the same, or just in the reverse order?
It's a little bit more, some it has some peculiarities. So the opposite way. Okay, we have a vector that is orthogonal to all the. So okay, we have a vector v, which is orthogonal to all the GEVs for all e's from some set of E. Okay, this is equivalent to V being orthogonal to the orthogonal to the span of those vectors.
I'm sorry, why are we proving this right now?
To show actually why we.
Can we state the? I'm really lost. Can we state the
90%
result?
is lost.
Everybody is really lost.
Okay.
Let's just
Let's just get the result and get to the point.
Okay, let's get to the point. So basically, okay, this theorem shows us that we can actually really search among one-rank representations. So we can actually restrict our classifier to be just scalar multiplication by 1. Okay, and for the linear case, but we can generalize for any other cases. And this is the illustration of the theorem statement. Basically, we can see that the solutions of our invariant linear predictors are they lay on the intersections of ellipsoids, where ellipsoids are induced by this equation for the MSE loss. For the MSE loss, this equation will be just ellipsoids, because it's squared function. Well, never mind. I understand that I'm also tired. It's okay. But actually, this shows us that we have a very a big drawback of assuming linearity of our classifier, because 0 is always a solution. And okay, we will not dive into details. It's just a bad thing. And the authors say that they will consider the nonlinear case in the future work. Okay, but in this work we assume linearity of our classifier. And finally, we just rewrite.
Why 0 is solution? Because it's orthogonal to any vector.
Why 0 is solution?
Yeah.
Well, because 0v is.
It's orthogonal to any vector.
Yes. Yes.
But can we just exclude this degenerate case?
Well, basically, the authors say that in our IRM, this empirical risk term will tend us from the 0 representation. So it's okay in practice, but they are going to consider it in future work more in more details. Okay, so we just rewrite the penalty that we introduced earlier in a general case, in this case, because those two coincide for MSE loss. So if we have our risk as just squared error, then the gradient with respect to the classifier would be this equation.
Excuse me, why we don't exclude the vector with 1, 0, 0, 0, 0? Because it's for using the same reasoning, we can, as for 0 point, we can exclude also this vector, because it's like it seems unuseful for us because we don't take into account
yes.
the rest of the.
We're excluding this because you see in our practical formulation of IRM, we have a direct mapping from inputs to outputs, and here we need this dummy classifier, which is just a scalar multiplication by 1, just to take the derivative, just to put it to PyTorch so it can autograd and count the derivative, which is our regularizer, which seem to be able to help us achieve invariant solutions. Okay, now we will skip this, don't worry. Invariance, causality, and generalization. Well, we can believe that IRM promotes low error and invariance across training environments, okay? But we have several questions. does it promote invariance in all environments? Does it promote low error in all environments? How do those things actually connected, like causation, statistical invariance, and out-of-distribution generalization? Well, please see the article for details, because, well, I can explain it for those who are interested after this talk. But the details are really interesting, because the authors provide they answer all those questions for linear case. And even for linear case, they require differential topology to answer those questions. So if you're interested, please.
But the answer are like maybe.
No. The answer are these big theorems that says when.
Sometimes.
Yeah. Sometimes.
Under certain conditions.
It's like a proof by elimination, yes?
Yeah. Something like that. Okay. Experiments, our favorite. So the first one would be a little modification of our first example that we had on the blackboard. Okay, so this is just a little bit more specific structural equation model. We have also now like a hidden latent variable here, and a little bit more difficult equations. They also consider 8 different experimental setups, which each one is encoded by these 3 parameters. So the first parameter is scrambled or unscrambled observations. That means that if we can observe X as they are or after some orthogonal transformation, is experiment fully observed or partially observed? So basically that's our hidden variables do mess into our model or not. And homoscedastic and heteroscedastic, this is just the position of noise. And those are the results. So let me explain what you see here. For each of 8 experiment types, you see, for example, FOO is fully observed, homoscedastic, unscrambled, okay? So for each of these 8 experiment setups, they plot 2 bar plots. The first one is for the causal error, and the second is for the non-causal error. So this is basically the error for the coefficient of x1 and the spurious coefficient x2. So they say that, as you can see, IRM, which is green, IRM has the lowest causal error in all the experiments, but sometimes it has worse loss for non-causal variable than invariant causal prediction. And the authors say that their method is much better. ICP is just more conservative, because we are focused only in learning causal predictors. So believe me, it seems that IRM works. And to prove it even better, I would like to introduce you the MNIST experiment, of course. We're coming to the two-label spurious correlated MNIST. We have a binary label, which is 0 for first 5 digits and 1 for the rest 5. And then we also flip our labels that were received this way with a probability 1/4. It's like a noise in our environment. And then we introduce this spurious correlation between the color and the output. So we will color our image into green if we have color index 0, and into red if we have color index 1. And this color index is received by flipping our label with some probability which is dependent on the environment. Okay? So the setup seems to be rational. And in training environment, those probabilities of flipping are relatively low. So this correlation between color and label will be very strong in our training environments. However, it changes from environment to environment. So we can hope that our invariant predictor will notice it and get rid of this spurious varying correlation. And for our testing environment, we on the opposite, set this probability to a high value. So our predictors that use this color feature for their prediction will fail. Okay? And here are the results. They just compare against simple empirical risk minimization setup. So as you can see, ARM, as it can be anticipated, has a very low training loss because it uses color, but it absolutely fails on test environment. Whereas IRM seems to be more or less robust. And here we have, for example, several other baselines. Those are random guessing, which is 50-50 as always. Optimal invariant model, hypothetical. So hypothetically, the best model could achieve 75% accuracy because we have this random noise in all environments. And they also provide an oracle model. It's like empirical risk minimization on top of grayscale images that do not hit the color, so they're invariant.
What's our model? What model?
Is it just a linear model of images, or is it?
No, it's multi-layer perceptron.
Why do you need this 0.25% of
Well, it's like hidden variables that we cannot observe, but that okay, it's like a noise. Okay, just a noise.
Why do you need it?
I don't know. They just set it for the generality. So in general environments, we can have noise in our outputs that we cannot do anything with this, and so.
And at the training stage, just two environments are known.
Yes, we have two environments with low, but
We establish a kind of invariance with respect to these environments, right? Which allows us to perform more or less okay in the case of a third environment.
Yes, and as you can see, the testing is it's absolutely different from the training environments. It has, and also I would like you to think with me about this plot.
And a question: do they have domain adaptation baseline? Basically, it's the same thing, but
No.
Such that given their representation, you cannot distinguish between the two training environments.
I also had this question when I read this paper, but it seems like they're not too fair with us.
I have kind of strong impression that under the code, if you just look at the method, it's very similar. It will be super similar to one of the techniques.
But
something done with the one which from Victor Lempitsky and US Afghani, which is inverting gradient. It be super similar to that.
Well, instead they provide the discussion on that topic.
Is this experimental stuff with this flipping usual, or are they the first one who use it?
They're the first one, yes. That spurious colored mnist is their invention. IRM and the color mnist.
It seems that without this 25% probability, they had not very good results, and they didn't want everybody to know.
Maybe. Well, maybe. We'll discuss it. We can discuss it after the talk.
They explicitly constructed a task where there are very powerful spurious correlations to be had.
Spurious correlation in the color, not in this flipping probability. That's why I don't understand why we do it. Why?
Probably your hypothesis is pretty close to the truth. I would assume that without this noise, the results were pretty bad.
Maybe they need to break ERM. Otherwise, ERM just works.
Maybe.
It's just you need to screw up to make it not work on this.
Because with this noise, I think that we're making pixels less informative. We're making colors more informative.
Okay.
And we make explicitly to our ERM classifier to rely on color.
Okay, and
That's a masterpiece of experiment design. How to convince everybody that your bad model is actually good. Yeah.
Well, as a reviewer, I would be so pissed off about such an experiment. I would go crazy. Sorry. It's just any cheating.
That's why you added shared tips.
Okay, so one more figure. The authors also provide the probability of output being 1 conditioned on the logits. On the h is just phi of x. It's just the last layer of our network. Okay, so h are just logits, and they plot the probability of output being 1 against the logits, and they claim that, as you can see, empirical risk has absolutely different distribution for the testing environment, whereas Oracle has the same distributions, and IRM, like, too has the same distributions, but I actually do not understand, and I couldn't find it in their code. How do they plot the probability of output being 1 against the prediction of the network, against the logits? Maybe some Monte Carlo estimate, but they didn't make it clear, actually. So those are just some more plots, if you're interested. Okay, and finally, an information-theoretic view. That's literally 5 minutes. So that information-theoretic view, I encountered it in this blog post, and I found it really interesting idea, really interesting viewpoint for this concept. So basically, the author of this blog proposes to look at our task in general, like this, this Bayesian network, where we have environment, we have some latent variables or noise, we have causal features and spurious features, and of course output. And our main assumption is that given inputs, given causal inputs and noise, we're independent of the environment. So this is the main assumption in such a graph representation of the paper. Okay? And our task is to learn such representation of our inputs that our output is as much as possible independent of environment, and also this representation should be somehow informative about our outputs. But that's very close to the informational bottleneck, isn't it? Because in informational bottleneck, we're trying to learn such a representation of our data which takes the least from the inputs and gives the most to the outputs, right? And for this case, we can rewrite IRM principle in this form. So basically, again, we're trying to maximize mutual information between our outputs and representation, but we subtract the mutual information of our outputs and environment given our representation. So something reasonable, right? It's very close to the penalized version of IRM that we already see, that we have already seen. But the author goes even further and says that we can actually receive something like this from the informational theoretic point of view, the equation of this type. And he does the following. He represents the mutual information, the conditional mutual information on the representation of our outputs and environment. He does some math juggling. We will not dive into details, but it seems to be reasonable. He explains it in more detail in his blog, but with some mathematical juggling, we can approximate mutual information between our outputs and environment with this equation. Then, instead of minimizing here over all the parameters of our predictor, we can minimize only in some neighborhood of this value, theta. And this actually is the negative. Here we should have the 2 on top. It should be squared, but the author seemed to mistyped it. So this seems to be like reasonable thing for small epsilon values, right? And finally, yes. And finally, we add the empirical risk term to this lower bound of our mutual information of our outputs and environment, and add minimization by representation. And the final thing would be to notice that every global minimum of this term is local minimum of this term, because when the gradient is 0, it's a local empirical risk minimum. And then we can combine those two minimizations into one and achieve something really similar to the IRM. So it's like empirical risk plus some gradient squared regularization. So this is just like a side point.
Could you please comment the transition from the first to the second slide?
This?
It seems like a very rough approximation.
Yes, that's very rough. Yeah, and the author also says that it's not optimal, but he says that if we assume that they are like nice and convex, then everything should be all right here.
Seems that they just want to get an answer they already know.
Well, basically, yes. I also think so.
How do we get the third line from the second?
This?
Yes.
Because this is just
The gradient.
yes, just a minus gradient. Okay, so let's come to the summing up. Okay, we want to learn some robust predictors that are based on true causal properties on our data and do not pay attention to the spurious correlations that present in our data. For that, we notice that invariance and causation are quite related things, and we can leverage their connection by promoting out-of-distribution generalization, as we've seen in the beginning. Also, we assume that our data are sampled from different separated environments. They can vary, but all of these environments preserve the same causal structural equation for our outputs. And finally, the IRM principle, once again, we try to find such a representation of our features that the optimal classifier on top of it would be optimal simultaneously in all environments. And here is the practical version of IRM. So, thank you very much.
Why do you have always in green formulas IRM version 1? Are there version 2?
No, that's just version 1, because there are so many things that are for the future directions. They leave they leave a lot of things for future studies, like considering nonlinear case, like answering those questions for nonlinear case, or something like that. So this is just a concept, the first one that was proposed, and it seems that this thing will develop further on.
Okay, any more questions?
So, wouldn't you say that like spurious correlations are simply an issue with the fact that we have a very high information input and a very low information target, right? If our targets would be like more complex, as in you'd be asking, so instead of just saying cow or camel, you'd be saying cow, cow eye, cow horn, grass. You're asking the system to learn about everything there is in the image. And by learning about everything there is in the image, you can't spuriously correlate. As in, like when I look at a picture of a cow, I can also say that this is a grass, this is the cow horn, this is the cow like skin, mouth, whatever. Like I decompose this image into a hierarchy of different things.
Mm-hmm.
So if you like ask the model to learn all the same information, then presumably you might ameliorate, like you might decrease the problem of spurious correlations, because you'd say, oh, this is a grass and this is sand.
Okay, yeah, I understand. You say that
here's the cow and here's the background.
You say that when you make your problem more complex, more specific, then you will have less spurious correlations, yes? So you will not care about the background color if you are just concentrating.
I'm saying I want the model to learn more, and by asking the model to learn more, it stops, like, okay, like if I'm learning, like if I just go and learn something completely new that I've never ever seen before, like let's say I'm trying to, talk about Chinese Chinaware or something, right? And I don't know anything about Chinese Chinaware. So maybe I will latch on to the most descriptive features, which are also spurious, because I don't understand the true underlying process. But to understand the true underlying process, I need to understand all these details and then reconstruct the more general worldview from the details. So if we ask the model to do something very similar, we might stop latching onto the most descriptive features and try to actually understand the underlying process.
Well, you see, those spurious features are changing, and those the shape of like I don't know, the horns, the eyes of colors.
Yeah.
They are stable. Every cow has horns of similar shape. So this is a stable property. This is like a causal invariant property.
Okay, fine. So simplest thing, you do an object detection. You teach the model to do object detection plus object classification. So it has to both say what object this is and also cut the object out from the background. This way you teach the model that there's something in the image and something in the background. Therefore it should learn to detect the image.
It's more what's seen in very ordinary information analysis.
Yeah, but then you ask it to do more things. Ask it to do more things.
To predict all the pixels? Yeah, from all the pixels?
Yeah. Well, I mean, like, ask it to do what a human does.
So, very stupid question. How it can be proven that these laws, like your ROD, is will cause you to learn the causal predictor. So are there any guarantees?
Yes, that's exactly what we skipped. In this this question that you're asking, I see, and the authors provide some they shed some light on this, but again for specific linear case, and this is highly non-trivial. So they apparently show that yes, though that ROOD, it's something that works, that actually helps us to find true causal predictors. But to prove that, you need to really dive into details. So this presentation is just something like hand waving. Yes.
How many pages
Okay.
do they have?
What?
How many pages do they have in the paper?
31. Very nice. Very nice.
Was it accepted somewhere?
What?
Was it accepted somewhere?
I don't know. I just know that this is Facebook research. So there.
Your lip submission?
No, you see, this is more like a philosophical paper. They have a very large. First of all, they have a lot of theorems, and those theorems are not trivial at all.
This is not philosophical paper.
This is the first point, and about the philosophical point, they constructed their discussion section as a dialogue between two students that just read this paper, yes, and they just eager to discuss this paper with each other, and well, actually, I've never seen students that would talk like this, but they.
You haven't seen papers written like this as well.
I've seen one.
Yeah, with introduction, like a dialogue between the student and his supervisor, and what they should do.
So yeah, and those two students discuss a lot of philosophical things about why this makes sense and when this makes sense, and how this is connected to our life. And
It's like what Platon dialogues.
yes, not Platon, Socratic dialogues. They
This is Platon.
yeah.
Because of Socrates.
Yeah. Well, they call it like Socratic dialogue.
I ask, show me imaginary results, and if it works, then you can do whatever you want. And if it doesn't work, then like please be like within the
Not everything
regular
always run in ImageNet. Come on. everything has to always be run on image. Some things just, somebody might not like.
No, okay, let's continue this discussion after seminar, not during seminar. Any more questions to the speaker? If not, then I have one question to the audience. Who knows who will be our next speaker this week? You? Good. Maybe you also know the title, the topic.
Yeah.
Good, please mention.
So I can give some.
Don't start with a dialogue between two students.
Just the title.
Okay, that's the title. Why do narrow mass learn and generalize? That's the title. Okay.
Okay, this could have a dialogue.
Okay, let's make it.
Let's take the speaker.